forecasting?
Thanks. Yes. So, although it's got forecasting in the name, this is somehow a talk about mathematics, or a mathematical talk. So I'm going to tell you something that you at least intuitively already know, and perhaps if we get time, I will tell you something about how this implies something that you also intuitively already know. So let's imagine that we are in a some sort of deterministic chaotic dynamics, and this is, I mean, somehow this has all the nice properties that we might want, that it's ergodic and that it mixes. So somehow we expect that as we run our system for a long time, we will have some kind of average statistical behavior. And this statistical behavior is going to be modeled by a probability measure, which we'll call rho. And so this, typically this has some nice structure to it. But the and I suppose, the result that kind of is the key to saying anything else about the sort of, properties of this system is some kind of, let's say, quantitative decay of correlations result. So if we have some, if we have two observables on our phase space and we look at their covariance, then as we sort of take the sort of time between two times we make these observations, we expect that these should become independent at some rate that we can quantify. But basically, it should decay exponentially. And then this is the formula that this is the sort of result that we want. We can actually think of it a little bit differently by saying, well, okay, if we take this one of these observables and we think of this as reweighting our measure, sort of kind of tilting it, then we should expect that we get some, well, okay, that if we look at the sort of forward expectations, the kind of, let's say, forecasts of our function A with respect to this tilted measure, it should decay back to the sort of this rho, the sort of background noise. So, for example, in this picture, we have this, we've kind of, well, taken a bunch of observations sampled from the a bunch of samples from this tilted measure, and it will converge back to the original measure, which is obviously mostly supported around the mean of this observable. So yeah, I mean, yes. So somehow, okay, mathematically, we can talk about this using transfer operators, which we won't talk about really in this talk. Yes, this is kind of more or less a fundamental thing that we know how to, well, if we know how to prove anything about a system, this is the thing that we want to be able to prove. And okay, I suppose it's quite intuitively obvious. But we could also ask, well, what about other kinds of initial information? Perhaps we have something more precise than a sort of, a smooth reweighting of our measure. Maybe we might, know, for example, we might know some coordinate of the system at time 0 exactly, and we might want to ask, well, do we lose all that information as well? And okay, so that's kind of what I want to, what we'll talk about now. But somehow this naturally comes out of sort of filtering. So okay, so obviously we make an observation. We have our dynamics X, which is in again, there's this chaotic thing, and we make some observation of it. And of course, it's very natural if you have say a big system of PDEs or something, that this is going to be partial observation. Okay, but then we have some observation noise, and we would like to make some kind of forecast of this idea. I mean, let's say in a probabilistic way. And okay, so of course, as you all know, the kind of perhaps the statistically best way to do this is using a Bayesian filter, where we just, we have some distributions, we're not discretizing that in any way, and we just apply Bayes' formula. So, okay, so somehow we're interested in, I mean, again, in Bayes, applying Bayes' law, and we get that, supposing that our noise has kernel P sigma, then we can write posterior as just the prior times the times the kernel, which we can perhaps assume to be smooth. Okay, well, this is we could ask what do we choose as our initial posterior? If it's our first observation, we can assume that we know nothing about the system, just that it's presumably at equilibrium. And okay, so the natural choice of our posterior is this physical measure, this background noise that we converge. Well, it's kind of background statistics that we'll end up with. And so, okay, let's imagine that we have this, we're in 2 dimensions here, and we have this, well, a system that generates this kind of attractor. So our initial condition would probably be, our initial guess, our prior guess would probably be some distribution, well, a distribution that is supported across the whole black area, which is the attractor of the system. If we make some observation, then well, our Bayesian posterior will be something that is kind of concentrated around this line, but is sort of, I mean, somehow smoothly varying in terms of its density around it, but still supported. I mean, still supported on the attractor. Okay, so this is our Bayesian guess, and then we say, okay, well, we want to forecast what our system's going to do into the future. I mean, of course, you know, on this sort of little 2-dimensional, you know, linear thing, it doesn't won't mean much, but we can imagine. Well, basically, what we do is we push this measure forward by the dynamics in the way that you do, and okay, well, perhaps over some short times we should get some information out of this, but over long times we know that, well, we're pushing forward. Okay. Our prediction is pushing forward the this kind of reweighted version of our SRB measure that we saw in the previous slide, and well, we can say, okay, this is the sort of prediction of some function A is going to look like, well, I suppose the sort of future estimate of A times this reweighting, and from this kind of, if our system has exponential decay of correlations, then we know that this is going to converge back to, well, I suppose the integral of A times the integral of this thing, which is going to be a probability measure, so that should be 1. So somehow our future forecasts will lead back to the original one. This is, I mean, somehow quite, I mean, the thing we all know. And yeah, so if you actually do that, you see that this is what the kind of the difference, like the difference between the prediction and the background, the kind of climatological expectations in the bottom figure over time. But then we could ask, well, what if we improve our observations? So we make the noise in our observations smaller. So then when we make our observation, we get something here that is perhaps more concentrated than in the previous case. And well, okay, we could just keep reducing the noise error, and we can see that we get better, we get like, say, some predictive improvement over longer timescales. But as you can see, even when there seems to be at least some kind of long-term convergence. As we make our noise smaller and smaller and smaller, there seems to be some line here that we end up converging to. And okay, well, we could ask what happens as we make our observation noise 0. Obviously, that's not particularly physically reasonable, but it sort of tells you about some kind of limiting behavior of improving the quality of the accuracy of your observations. And well, okay, in the end, we end up with some measure that is just supported on the actual line, on the line of, you know, the actual, like, h of x is equal to the observation we get. And so somehow it is possible to figure out what this limit is, which is this black line. And as you can see, this limit of this measure here, this measure with the orange dots, I don't know if you can see it, is well, if we look at if you push that forward, we see that it also decays. The predictive power decays back to the climatological forecast at some exponential rate. And okay, yes. So I mean, you have to do some kind of careful numerics here, but you can take a Monte Carlo sample of this And yeah, this seems to happen. And if we I mean, somehow this is not something that mathematically you would expect, although perhaps it's not unbelievable. And so if you, in the following, I'm going to call this conditional decay of correlations, because we can think of this here. Sorry, we can think of this measure here as a conditional version of, like, the orange dots are a conditional version of the black, the conditional measure of the black dots on this line.
Sorry, I have a question. We need to change the minutes here. We cannot. So
Yes.
the second limit really depends on the initial organization. So if you use the invariant method, another divide that one on the left side.
So I mean, if you took a smooth initial condition, then
Yeah.
and I mean, I suppose if you're writing a common filter or something, it's what you always have to have. So yes, so okay, but basically, I mean, yeah, we have this behavior. We actually find this behavior. I can't do this. Yeah, that somehow our slices, our conditional measures will, as we push it forward, will actually fill out the attractor in a way that kind of happens quite quickly, or happens quite comprehensively. And okay, so this is, I mean, as I said, this is not something that we really know anything about mathematically. We can see that there's some cases where it doesn't work. You know, you can construct it. Suppose that you make an observation that basically is the effect that this that your system lies in some invariant set. You know, in that case, your system is trapped in this invariant set, and you're not going to mix back to the full system. But if you're, I mean, you know, if your system is ergodic, then somehow the set of invariant sets that you have are of measure 0, so you really don't expect to see this. Okay, so generally we could perhaps conjecture that this kind of decay, for if we make a sort of generic observation, that this observation won't be useful in forecasting way into the future, because we have this decay of correlations. I mean, for some time it will, but to infinity it won't. We can kind of show this for conservative systems, like, you know, sort of formally. There's enough regularity in the measures there, but if we have a distributive system, which is of course very natural in sort of geophysical problems, then somehow it's too irregular, and you know, our measures might look like this kind of Cantor, well, this histogram of a Cantor measure here. So if we actually try and so we tried to find some mathematical results, and we looked at these Baker maps, which basically they're linear in this, there's some x coordinate, and they're linear in that, they're just an expansion. And in the y direction, they're a contraction. And this is, I mean, somehow this is not this is perhaps the only system that I can get anything at this point. And the reason for this is basically just using the fact that the x component is linear. We can show actually for a very robust set of sort of observations. So this psi y minus x is the thing that we're observing, and well, okay, we can define it. This is something that people worry about, this conditional measure, and okay. So basically, if these contractions here are, well, basically, if they're not linear, if either the contractions are not linear or the curve, sorry, let's maybe start with this one. If either the contractions that are happening in the y direction are nonlinear, or the curve that we're observing here is nonlinear, then, well, okay, basically the sort of any kind of algebraic structure that we could have, any structure we have that could mess with this kind of conditional, this mixing result, isn't there, and we find that we have the kind of decay that we want. Okay, so somehow, I mean, this is saying that for almost any curve for these maps, we should expect, almost any observation for these maps, we should expect to see this. This is this is something we can prove. So we could hope that in general, this is the case, but it's not. Somehow the results we were using here is something from kind of fractals where they're using a linear structure, and in general you don't have linear structure. So well, it's a work in progress to see what we can say about it. It's perhaps worth saying, well, okay, in this case, when we were talking about this, we were just making one observation, and then we were trying to forecast based on one observation. This is not, I mean, in general, you're making a sequence of observations, and we know that if we make a sequence of perfect observations for long enough, somehow the Tarkin's embedding theorem tells us that we should be able to reconstruct our attractor, reconstruct our system, which lets us predict for all time. But we think that if your system is smaller than the number of positive, if the dimension of the total dimension of the observations you're making, if the number is smaller than the number of positively F-knob exponents, it seems quite natural. But so the number of positively F-knob exponents, just in the dimension of your attractor, it seems quite natural that you would get this kind of correlation decay result. And in fact, perhaps it might actually say something about how ill-posed the Tarkin's embedding theorem is. That would be something worth thinking about, maybe. But this is all speculation, really. But okay, so how much time?
5 minutes.
Okay. So I suppose, given that, I might tell you one thing that actually this conditional decay of correlation result implies. There's some evidence for this mathematically. And this is the problem of linear response. So again, something that probably everyone kind of assumes, that if you sort of make dynamical perturbations to your system, and let's assume that they're time invariant, so you just, sometime in the past you change your, in the absolute distant past, you sort of change how your system evolves just by some little amount. This will change this will change your statistics. It will change this measure, which approximates, which encodes your statistics. So it's okay. So it encodes changes statistics, and we can ask, well, okay, if we make an epsilon perturbation to our map, are our statistics going to also change by some order epsilon amount? And this is actually worth asking, because we can actually predict the change in our measure from the unperturbed system, then we can do some Taylor series, and it's all good. And we know that this works for a lot of systems that we're interested in. So we know that this works for a lot of real systems. Conservative systems and stochastic systems, and so therefore you might think, and for uniformly hyperbolic systems, so kind of most things. Well, we can also find examples of distributive deterministic chaotic systems where this doesn't work. So the logistic map, they've shown that you can't get. But for this, this really simple system, you can see that you get some kind of your measure, which is plotted on the y-axis, versus the perturbation here has really you can't get anything, at least for the chaotic points, you can't get any kind of nice smoothness in this function here. So we can't do linear response theory, which somehow in physical systems people have tried and had reasonably good success with. So they've looked at global climate models, for example, and found that the kinds of results that you get out assuming that you have this derivative in your measure is, they seem to give the right answer. So we think that actually most systems, even though there are some examples of very simple systems where it doesn't work, we think that most general systems it should work. But we don't have any way, we can't prove this. We don't really, not even that we can't prove this, we don't really have any good understanding of the the mechanisms behind what causes linear response to fail for simple systems, simple, non-hyperbolic. So that's just almost anything. Chaotic systems. Why does it fail for the simple ones, and why does it work for the why does it work for the high-dimensional ones? So somehow this conditional decay of correlations makes it work, and I didn't think I'd have time perhaps to go into it, but essentially the problem is if we imagine that this attractor here is that I keep telling you about this so-called Losy attractor, which is somehow a simplification of the Henon attractor. Well, okay, so most systems involve some kind of folding as well as stretching, and this actually is where the problems with linear response come, because you get these kinds of bends in your measure, in your attractor, which I'm sure you've all seen at some point. And these are where linear response kind of falls apart. And so in this case, we can actually say we can really locate. We can say that these bends in the attractor actually come out of some. Well, they all lie along lines, right? So if we condition our attractor, if we condition our measure on these lines, somehow these like the behavior of these is the key to whether we have linear response. And conditional decay of correlations tells us that these lines, so the measure on these lines behaves in a generic way, and this is enough to tell us that, well, okay, if we have conditional decay of correlations, if this works, then we have linear response. So this is a result of these piecewise hyperbolic maps, and we see that we do actually get some kind of differentiability in this in the parameter versus the in the measure versus the parameter. And so there's been this. So David Rurel has this conjecture out there that says that if you have actually general systems that are non-uniformly hyperbolic, then you expect that if the dimension of if the sort of stable dimension of your attractor, so that's the dimension of your attractor minus the number of positive Lyapunov exponents, if this is more than, I don't know, like 1/2, then you expect to see linear response. So somehow we don't really know what to do with that, but rigorously, but this perhaps might lead to some. Hopefully, this might lead to some work on that, and certainly it's kind of diagnostic that if your system does have this, which, as I said, we expect it in general, but you can sort of cook examples in infinite dimensions where it doesn't quite work out. Then you might be able to say something about when you have linear response. But I mean, again, that's all that is. So I suppose to summarize, well, there's this kind of property of statistical property of chaotic systems that somehow tells us about what happens when we make very good observations in the long term, and it tells you something about this other thing, linear response. And we're not sure how to prove it, but well, it's prove much about it, although we have some results. But I mean, somehow it might be worth thinking about. And I'd be interested if anyone has any places where this turns up. So.
Thanks very much. Do we have any questions?
Yeah, so my question is on your last result with the Losy map. I was wondering if, since it seems that it's working because you have these lines on your mapping.
As in, like the fact that the attractors are straight lines, or
yeah,
that's really not necessarily. I mean, it makes the numerics easier, but not necessarily. No, you can. It should. So I mean, actually, proving this result, saying that suppose you do have this phenomenon that implies linear response, that has that is something that would, I mean, that would work if it wasn't linear. You can, the fact that it does work, I mean, so actually at some level you expect the fact that it's linear to mean that it will cause you more problems, because, I mean, for these Baker's maps examples, go back. Here we're actually assuming that everything is nonlinear. Like, having nonlinearity makes your life easier. Like, it won't work when everything's linear, because there's some structure there that's preserved. And I mean, you know, you could imagine like the sort of, you know, the classical Cantor set. If you multiply everything by 3, then you'll get the same quadratic words. I mean, if you imagine that this slice here to be like the Cantor set. Yeah. So actually, linearity shouldn't make it invalid.
I had one. Just to get my microphone straight. So in the same slide, actually, can you explain a bit more the graph on the right, and then what you mean with slightly extended decay approach?
So okay, so the graph on the right is a plot of, I mean, so it is a plot of like we observed this map, a dynamical perturbation. That's what we got there. And then this is sorry. Okay, yeah, so dynamical perturbation, average being plotted. The blue line is the black line is the true. A is just, I think it's like X or something.
Observable.
Yeah, they're observable, yeah. Yeah, so you can see there's this black line. The blue line is the one that we get if we use linear response theory. And okay, so this window here is. Oh no, hang on. Do I need a microphone? No. Okay, so good. All right, good. Okay, so the blue one is so the green one is. I mean, if you sort of use this theory that Ruel's sort of hypothesizing, you would say that okay, the black line should be C1 plus this stable dimension thing. So the dimension of the attractor -1, and okay, so you can try and put a window in, and you can see that.
Ds is the dimension. What's ds? 1 plus ds.
1 plus ds. So it's saying that the derivative is ds holder.
Okay.
And so that's, I mean, that's what. Yeah. Just like the Taylor error. Taylor approximation error. Okay, and then the slightly extended, it's just you need, instead of like you need second order decay of correlations.
Any more questions?
I mean, so for this general result where you show that the conditional decay of correlation implies you a linear response. I mean, why you say it's formal, and for which kind of dynamical systems you can do something like that?
Okay, so by formal I mean that the susceptibility function decays to 0. So that, I mean, to compute this linear response, you basically sum up the response if you perturb it at a time n steps behind, how that changes the statistics at time 0, and then the time independent version is the sum of all of these. And so what I prove is that all these sort of these things, as you go to 0, decay, as you go backwards in time, decay to 0.
You don't get the spectral gap. You cannot invert it.
It decays exponentially to 0. Yeah. But I mean, this is somehow, technically not the same as saying that the response is there is actually a linear response. You're just saying that a derivative formally exists. And this works for piecewise hyperbolic maps. So these are piecewise uniformly hyperbolic maps. So it's like they're anisotropy, except that there's some line where they stop, which in fact is this purple line here, where they stop, where they aren't anisotropy. There's like a lack of differentiability, which is what causes all these problems.
No more questions? All right, thanks very much. I guess we come back at 2.
We can stay here for lunch,
Yeah.
so.
Today we're lucky.
Lunch is downstairs, and we reconvene. Is this at 2 o'clock?
Yeah, yeah.
Okay. But I think before we go for lunch, we should thank all the speakers of the session, and also thank Julie Besac for chairing this. Thank you very much.